are now just going to look at some applications for logs. So they're not just totally made up things with no purpose, they have a place. The things that we're using today, mostly I'm going to be giving you formulas that if I asked you to solve one of these problems, I would give you that formula as well, so we're not necessarily memorizing a ton of formulas. So at the top, there's quite a few that we're going to look at here. The first one is if we're talking about pH, so you do this a lot in science classes, talk about pH if substances are acids or bases. Well, it's actually a mathematical calculation. So pH is negative log H3O+. H3O+ is your hydronium ion concentration, and so we can use that to calculate the pH of a substance. All right, so we are going to jump down to example 1 here. Find the pH of a solution with H3O+ equal to 2.5 times 10 to the negative 4. Most of the time that's going to be written in scientific notation when you see it. So we're just using our formula. pH is a negative log, and the H3O+ is 2.5 times 10 to the negative 4. And then we plug that into our calculator. So negative log 2.5 times 10 to the negative 4. And usually pH we round to 1 decimal, so what do we get? 3.6. 3.6. Is that one okay? Pretty straightforward. You would be given that formula, so you just have to plug it in. Then find the hydronium ion concentration of a solution with a pH equal to 7.1. So this time I know my pH. But I'm looking for this H3O+. What would we have to do here? Well, we can't just straight divide the entire thing. Okay, first let's move that negative. So if we divide by negative 1. Now, if you have a log on one side, what do we have to do? Whatever it is. Yeah, so if the base isn't written, what is it? 10. So it's 10 to the negative 7.1 power equals this H3O+. If you put 10 to the negative 7.1 in your calculator, you get a long decimal. It's like 7.94328, blah, 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 blah. And then at the end it has E negative 8, so that's scientific notation, so times 10 to the negative 8. So the H3O+, like we already saw in part A, is usually written in this scientific notation. Questions there? our next one. Exponential growth and decay. So this one, the formula varies a little bit. When I talk about growth and decay, do you guys know what I'm referring to?
On the graph.
On a graph. So growth would be, it is going up. Decay would be going down. We see it a lot, like when you're talking about substances, we know that, you know, if you take banana peel and throw it outside, what's going to happen to it over time? It starts decaying, right? There's less of it there as time goes on. Likewise, some things, as time goes on, you get more of them. So that is growth and decay. So growth just means that as time goes on, we're getting more of a substance. Decay means we're getting less. So typically this is written in terms of a time. It's A sub 0, so like our starting amount, E to the KT. So A of t is the amount you have at a given point in time. A sub 0 is our starting amount. E is that number on our calculator. We know it's like a 2.7 and so forth. K is a constant. T is the amount of time. If your constant is a positive number, that would be exponential growth. If it is negative, that's exponential decay. So let's look at this one. If 800 grams of a radioactive substance are present initially, and 2.5 years later only 400 grams remain, how much of the substance would be present after 4 years? Okay, this isn't just like writing the equation of a line, because as time goes on, it's decreasing at a different rate. It's exponential growth or decay. So we have to create that exponential function for it. So to get that equation, we need to know the A sub 0 and the K. And then we could calculate the amount at any given point in time. A sub 0, what did I tell you that represented? The starting amount. How much did we start with? Okay, so I know that part of my equation. I need my K. So to do that, I can use this information. So 2.5 years, 400 grams, that's kind of like a point that we could use. So the amount at that point in time was 400. My initial is 800. E, we're trying to find K, but at that particular point in time, when we had 400, the time was 2.5. So far, so good? So then, we can solve this. What would we have to do? But can we multiply the E?
Would you divide?
Yes, let's divide by the 800. So we get 1/2 equals E to the 2.5K. All right. Then we need that 2.5K to come down. What do we do when we're solving these exponentials? Yes, we have the natural on each side. And we know that's helpful because the exponent comes down. And what is the natural log of e? 1. So that can drop. Divide by 2.5. So natural log of 1/2 divided by 2.5. And my constant is negative 0.2773 if you round. So that means my actual equation is 800 e to the negative 0.2773 times t. Is this growth or decay? Decay. Questions here?
What did you say K resembled?
K is the constant. It's basically giving us a rate.
Okay.
So we had to use the 1 point we had to solve for that K.
Okay.
And now we can answer our actual question. How much is present after 4 years? So what's my time? 4. So if we plug that in, we get 263.86 grams remaining. It's decaying, we have less as time goes on, and we get our equation. I want you guys to see if you can set up the next one. So I'll give you a few minutes, see how far you get. Our present initially. So what does that 600 represent? So we know so far the equation is this. We need to find K. And 3 years later, only 300 grams remain. Sometimes that 3 years is called the half-life. It's how long until you have half of what we started with, just as a side note. So we know we have 300 equals 600 e to the 3k power. Divide the 600. Then what did you do? Exponent comes down, the natural log of e is 1. So we have to do the natural log of 1/2 divided by 3, and your constant is negative 2.2310. So the amount we have at any given time is 600 e to the negative 0.2310 t. That's our equation. Then we want to know how much we would have after 6 years. So we just plug that in. And did you get 150.04 grams? Any questions about that? Okay. Next formula. One that we have seen before, I guess I didn't even put it on here. If you go back to the front, I do have your 2 interest formulas that we've used before. Your regular compound interest, and what was the second one? The PE to the RT? Continuous compounding. So remember, we've seen those before. I didn't make you memorize them. How long would it take for the money in an account that is compounded continuously? So when I see that continuously, that tells me I'm using the second formula. I want to know how long it'll take it to double. What is our rate for the R? We will use
0.0575.
okay. Did I tell you how much we started with? No. So we have a couple different options. We can keep it as a variable. A lot of times people just like to make up numbers. If I started with 10, how much would I end with? 20. Why? Yeah, I said I want to know how long till it doubles. So you could pick any starting amount you wanted and just double it to get your ending amount. Or you could keep P as the variable P and make your A at 2P because you're doubling it. My A is 20, P is 10, E to the 0.0575 T. What do we do first? So 2 equals E to its power. Add our natural logs. Natural log of E cancels. We have 0.0575 T. So if you divide, a T is 12.05. You could keep more decimals if you wanted, but this would be in years. Remember, anytime we're using this formula, T has to be in years. All right. Any questions there? One more of these. How long will it take $1,000 invested at 2% interest compounding quarterly to grow to 2,700? What formula are we using?
Compound.
The regular compound. What is my A? My A is ending amount, so it's 2,700. Your P is your beginning amount, so that's 10, or 1,000. Rate was 2%, so 0.02. What is N?
Court 4.
Yes, for how many times a year we compound. And we are looking for T. So if we plug in 2,700 equals 1,000. 1 plus 0.02 for 4 to the 4T power. If we divide the 1,000, we get we could clean up in our parentheses a little bit. We have 1 plus 0.02 divided by 4. So that's 1.005 to the 4T power. What will we have to do at this point? Do I have an advantage, natural log or common log? No. So whatever you want. Okay. We add the logs because then the exponent comes down. So to solve for T, we can divide by the 4 log 1.005. So a lot of the same equations that we were solving last week, we just have to go through the work of setting them up. So log 2.7 divided by 4 log 1.005. 49.79 years. Any questions there? Last thing I want to look at, the change of base formula. This is not one I would give you. So out of all of these, the only one that you really have to know is this. Log base A of m equals log base A, or sorry, log base B of m divided by log base B of A. It's saying you can take any log and change it into whatever base you want by doing log of the argument divided by log of the current base. This has to do with like exponentials. If I said log base 2 of 3. Okay, can we easily put that in our calculator? Now, if you have one of my calculators, there's a way to get there, but if you have the more basic ones, there is no option. So if we were setting this as an exponential, what that means is 2 to the x power equals 3, right? Can we get a common base? So if I'd given you this problem last week, you would have added a log to each side. Then the x comes down. So your x is log of 3 divided by log of 2. So log of the argument divided by log of the base. So this is how it works. So if you forget the formula, all you have to do is set it equal to x and work it out like we were doing before. So it's kind of a shortcut, but you don't have to have that memorized. What I would require if I asked you to do this on a test or quiz, because some calculators do it and some don't, I'm going to say if you don't show me the work, you get no credit for it. So your options are, if you don't remember the formula, you can set it equal to x. And say, okay, 5 to the x equals 7. Then what would you do? Add our log. So you have x log 5 equals log 7. So x is log 7 divided by log 5. And now it's to the point where everybody, no matter which calculator you have, you can type in log 7 divided by log 5. You get 1.2091. If you remember the formula, there is a shorter option. So if you have log base 2 of 0.1, and you remember the formula is just log of the argument divided by log of the base. So log of the big number divided by log of the small number. So you're welcome to just go straight there. Plug that in. Negative 3.321 then. Is that okay? Do we need any more practice with those?